Hi, I'm Anurag Sarkar from Northeastern University, and in this presentation, I'll be talking about work done with my co-authors at Cooper, where we combine the use of variational autoencoders with a quality diversity evolutionary algorithm map leads in order to both generate as well as blend levels for a number of different games. So what was the motivation for this work? Well, in recent years, variational autoencoders or VAEs have been increasingly used to generate as well as blend game levels. VAEs are an encoder-decoder based machine learning framework, and the way that these models work is they learn a continuous latent representation of the data that they're trained on, such as levels, and then new levels can be generated by sampling this representation. But it is because of this generation, which is usually done via random sampling, that standard VAEs are hard to control and aren't suited to producing a diverse range of levels in a controllable manner. Now, one way this controllability issue has been addressed is via the use of what are known as conditional VAEs. These are VAEs that allow you to specify labels at training time in order to generate levels having specific characteristics, and this has been shown to work quite well, but it comes at the cost of requiring a labeled dataset for training. In addition to that, the way you generate different levels is not by being able to explore the search space or the latent space, but by using labels to modify vectors that are still randomly sampled. A method that does explore the search space is called latent variable evolution, and this refers to the process of searching the latent space of the model using evolution to find vectors that optimize a given objective function. Now, this is shown to be effective both with VAEs as well as GANs, but it is designed to focus on finding a single optimal level that satisfies the objective rather than finding a diverse range of levels. Further, since this approach works with only one objective at a time, searching for different types of content necessitates multiple separate runs and/or constructing complex objective functions. Moreover, it is quite possible that the algorithm always converges to the same or similar optimal solution in each run. And so since we want to be able to generate a diverse set of levels, a good idea might be to turn to the quality diversity or QD class of evolutionary algorithms such as map elites, which are explicitly designed to produce a range of diverse content in a single evolutionary run. And moreover, QD algorithms have been used in a variety of recent PCG works in order to generate levels for several different types of games. And so the central idea of this work is to combine VAEs with map elites, and more specifically, instead of running latent variable evolution using a single objective optimization algorithm, to instead run map elites in the latent space of a trained VAE in order to generate and blend a diverse range of levels for a number of different games. So as a brief overview of our approach, it consisted of two steps. Step one involves training VAEs. So we train VAEs on levels taken from the video game level corpus or VGLC for 5 platformer games, Mario as per usual, but also Mega Man, Kid Icarus, Ninja Gaiden, and Castlevania. We also trained on a blended domain combining Mario, Kid Icarus, and Mega Man, and we refer to this part of the approach as blend elites. And in all cases, we train on 16 by 16 segments of levels in order to have enough training data, and this is a pretty standard practice in PCGML. And then for step two, for each of the 6 cases, we ran map elites using the learned VAE latent space as the search space, obtaining an archive of levels at the end of each run. And so our work contributes a hybrid PCGML PCGQD approach, combining the use of VAEs and map elites for level generation and blending. And to our knowledge, at the time of writing the paper, the first use of map elites to generate levels for basically the non-Mario games, so Kid Icarus, Mega Man, Castlevania, and Ninja Gaiden, and also blend elites, which is the application of map elites for blending levels across games. Now, it should be noted that there are other works that have run map elites in learned latent spaces, and in fact, this process was termed as latent space illumination in work done by Fontaine et al. That came out in AAAI this year, where they ran map elites and a bunch of its variants within the latent space of a GAN trained on Mario. And since the writing of this paper, there has also been some work in doing this type of latent space illumination using GANs and LoadRunner. Okay, so before delving deeper into our approach, just want to briefly go over VAEs and map elites. So VAEs, or variational autoencoders, are generative models that learn continuous latent representations of data. They consist of encoder and decoder networks, where the encoder learns the mapping from the data to the latent space, and the decoder learns the mapping from the latent space to the data. Now, while the latent space enables generation of levels via sampling and interpolation, it can also act as a continuous search space for evolving content. And this can take the form of starting with a population of randomly sampled latent vectors and optimizing an objective to generate the desired levels. And since the decoder, the VAE, is trained to generate levels from vectors sampled from this space, from an evolutionary computation perspective, we can think of the VAE decoder as effectively learning the genotype to phenotype mapping. And in this work, we perform evolution by applying maplets within this VAE latent space. Maplets is a quality diversity or QD algorithm. QD algorithms are evolutionary algorithms that search for a set of both diverse and high quality solutions in a single run. And they do this by defining subspaces within the evolutionary search space that correspond to different behaviors, and then return the solution that optimizes a fitness function within each subspace. In Maplets, these subspaces are referred to as cells and are defined based on a specified set of attributes referred to as behavior characteristics or BCs. And so for each of these cells, at the end of the run, Maplets returns the optimal solution within it, with optimality determined by a predefined fitness function. Now, typically when applied to game levels, the BCs are defined to represent different types of levels or different level characteristics, while the fitness function is used to capture playability-based constraints. So for our experiments, we used three sets of behavior characteristics. The two shown on the slide were both based on pairs of tile-based metrics. So first, we have density and non-linearity. Density refers to the number of tiles in a segment that aren't background or path tiles, so a measure of how solid a segment is, while non-linearity is a measure of how well the segment's topology follows a straight line. So higher the value, more uneven is the topology of that segment. And second, we have symmetry and similarity. So these are fairly self-explanatory. Symmetry is a measure of how symmetrical a segment is along both the horizontal and vertical axes, while similarity is a measure of how similar a segment is compared to segments in the training data. And the archive size for both pairs were determined based on the set of possible values that they could take. And so the archive for the first pair consisted of about 16,700 cells, while for the second one, it was approximately 8,500 cells. And these ranges are based on how these metrics were computed, and details on that can be found in the paper. Finally, our third BC was game elements, so here we focused on whether maplets can discover segments containing different combinations of elements specific to each game. Since the type of elements differs across different games, we use different archive formulations for each game in this case. And so here each archive cell was represented as an n-digit binary number, with n being the number of element types considered for that game, and 0 and 1 indicating the absence or presence of the corresponding element. And hence the archive for each game under this BC consisted of 2 to the n number of cells. How exactly this n-digit number is encoded for each game can be found in the paper, but just as an example, cell 11011 for Mario or SMB defines the space of segments containing enemies, pipes, coins, and breakables, but no question marks, as can be seen in the corresponding example segment. For our fitness function, we use playability as determined by game-specific A-star agents tuned using the jump arcs for the respective games. These jump arcs were derived from prior work by Somerville et al. And the fitness value was how far in the segment the agent could progress normalized between 0 and 1, where 1 indicates that the agent was able to fully traverse the segment using the jump arcs for that particular game. So the more progress that the agent made, the higher was this value. For Mario and Castlevania, progress was determined only along the horizontal direction. For Kid Icarus, only along the vertical direction, while for Mega Man and Ninja Gaiden, we considered both horizontal and vertical directions. For the blended Mario, Kid Icarus, Mega Man domain, or blend elites, we tested playability by running each of the three agents and setting the fitness to be the highest among the values returned by the three agents. So that brings us finally to our algorithm for combining VAEs with map elites. We first create the empty archive based on the chosen behavior characteristics or BCs. We then obtain an initial population of vector sample randomly from the VAE latent space and assign each to a cell in the empty archive based on the BCs. And then we run our evolution loop for the predetermined number of generations. So for each generation, we select parent vectors by choosing two occupied archive cells at random and perform uniform crossover and mutation to produce a child vector. We then forward this child vector to the VA decoder to obtain the level segment and determine the appropriate cell for it based on the chosen BCs. We also run the agent-based playability objective on the segment to compute the fitness score. And if the assigned cell is empty, we add this child vector along with its score. Otherwise, we do so only if the score is greater than that of the vector that was already in the cell. And this procedure is then repeated for the remaining number of generations. So on to our experiments. We had 5 games plus the blended domain, so 6 total settings. For each, we ran a trial for each of the 3 BCs, resulting in a total of 18 separate experiments. For each experiment, MapLeads was run for 100,000 generations using a mutation probability of 0.3 and a VA latent size of 32. And more details regarding network architectures and experimental hyperparameters can be found in the paper. Regarding evolution, the goal here was to see for each game whether MapLeads is able to discover playable levels and also to compare the behavior spaces for different games based on how MapLeads covers the archive over the course of the evolutionary run. So we looked at the QD score, coverage, and optimality percentage. So QD score is a standard evaluation metric for QD algorithms, which is just the sum of the fitness values of all occupied cells in the archive. Coverage represents the percentage of cells in the archive that were occupied at the end of the run, thus indicating how much of the search space MapLeads was able to find a solution for. And optimality further looks at what percentage of cells for which a solution was found had an optimal fitness value. Additionally, for blend elites, we wanted to see if there are regions of the archive where certain agents and/or combinations of agents do better. So if levels from certain regions are playable by a certain set of agents, that may indicate that those regions blend those specific games. So in the blend elites case, for each cell in the archive, we kept track of which among Mario, Icarus, and Mega Man agents were able to complete a segment that was assigned to that cell. And so that brings us to the results. So for both of the tile-based BCs, the highest QD score and coverage values were observed for blend elites, followed closely by Mega Man and then Kid Icarus, while for the game elements BC, the highest QD score and coverage values were obtained for Mario, Kid Icarus, and Ninja Gaiden. There's more discussion about these results in the paper, but the important thing to note here is that in most cases, if a solution was found for a cell, then the optimal solution was also found, as exhibited by the high values for optimality percentage in most cases. And this tells us that for the most part, MapLeads is able to find playable levels for all of the domains. But like we mentioned in the previous section, that in addition to playability, we also wanted to compare the behavior spaces for each domain. And for that, we examined what the archives actually look like. And so here we have the archives for the density nonlinearity BC. And we can see that MapLeads covers a smaller region in the left corner for Mario, Castlevania, and Ninja Gaiden compared to the much larger coverage for Kid Icarus and especially Mega Man and Blend Elites. And this can be explained by the fact that levels in Mario, Castlevania, and Ninja Gaiden tend to be less dense and more open than those in Mega Man and Kid Icarus, and this bears out in these results. Also worth noting is that the highest percentage of playable levels was found for Mega Man, and this can be explained by the fact that Mega Man has the most capable agent in terms of being able to move horizontally as well as in both directions vertically, thus enabling it to play through generated levels of more varied topologies. Similarly, KI had the lowest percentage of playable levels, and this may possibly be because the KI agent only moves vertically upward and cannot move horizontally, and so it is less tolerant to errors in generated levels since progress is primarily determined by jumping rather than just moving left or right. Moreover, the archive for Blend Elite seems to roughly intersect the regions covered by the 3 games Mario, Kid Icarus, and Mega Man. For example, the lower left corner region that is mostly unplayable in Kid Icarus is playable for Blend Elites, likely because it is playable in Mario and Mega Man. And there are similar comparisons made in the paper for the symmetry similarity BC, but the overall point here is that using map elites lets us compare different games in terms of specific behavior spaces and arrive at these types of insights. And as mentioned before, we also wanted to analyze the archive for the blended domain in order to see if different regions corresponded to different combinations of games being blended. And the way we examined this was by checking which agents could solve a segment from a given region of the archive. So, for example, if only the Mario agent is able to complete a segment, but the Icarus and Mega Man agents fail, then that segment is likely a Mario-like segment. However, if a segment is completed by both Icarus and Mega Man agents but not Mario, then we can expect that the segment blends both Icarus and Mega Man but not Mario. And so for each cell in the archive, we kept track of the agents that managed to complete a segment that was assigned to that cell over the course of the entire MapElites run. And these results are shown in these plots. So for both BCs, we see distinct regions of blending emerge in terms of agent-based playability. So for density nonlinearity, on the left plot, we see that the lower left corner is playable only by Mario and Mega Man, but not Icarus, suggesting that region to be a Mario Mega Man blend. Then as one moves outwards towards the top right corner, we encounter a region where levels are playable by all 3 agents, suggesting this to be a region that blends all 3 games, followed by a region that mostly blends Icarus and Mega Man, and lastly, an outer Mega Man only region. And similar observations can also be made with respect to the symmetry similarity plot. And so we finish with a few example generated segments. These are taken from the game element species, so the numbers under each segment refers to a cell in the archive for that game and represents the specific combination of elements present in the segment as discussed previously. So here we have Mario in the first row, followed by Kid Icarus, followed by Mega Man. And here we have similar examples for Castlevania, Ninja Gaiden, and Blend Deletes. And the specific examples for Blend Deletes here were playable by all three of the agents, that is, playable by Mario, Kid Icarus, as well as Mega Man. And so to conclude, we presented a hybrid approach that combines VAEs with the Maplitz algorithm for generating and blending game levels, and showed that this enabled the generation and blending of a diverse range of playable levels, in addition to identifying regions that blend specific combinations of games. There are, as always, several directions to consider in the future. In this work, we focused on just Maplitz, so in the future, we would like to study the effects of combining other QT algorithms with VAEs. We could also try variations of the current approach, such as using variants of Maplitz as well as more advanced VAE models. It would also be worthwhile to conduct user studies to see if players find a set of levels generated by Maplitz to actually be diverse. And finally, we would also like to incorporate Maplitz into ML-based co-creative and automated game design tools to enable designers to leverage both VAEs and Maplitz in designing levels. And that brings me to the end of the presentation. Thank you for your attention.